Hello friends, here in this video we will see the design procedure for a screw jack, and for that purpose here we have a diagram. Now screw jack is a machine which we call it as simple machine, which is used to lift heavy loads by applying comparatively small amount of efforts. Basically, when I talk about screw jack, it is used to lift vehicles. Now here, as we can see in the diagram, W indicates the load which is kept on this screw jack, and where this load is kept, that part is called as cup. Then we have the most important part of the screw jack, which is called as the screw spindle, which is here. The screw spindle is in between. Whenever we have a screw spindle, that screw will rotate inside a nut. So here we have a nut and screw spindle, they are in contact. Next we have a handle which we can rotate. Then we have the body here. This is the outer body of the screw jack along with the base. Next there is head of the screw jack which is attached to the cup. So these are some of the principal or important parts of a screw jack. Now when we are talking about the design of a screw jack, in that case the most important part which is to be designed, or you can say that is the heart of the screw jack, it is the screw spindle. So while designing the screw jack, the most important part, screw spindle, because it carries the load directly, the load which we are keeping on the screw jack. For example, it can be a car which is lifted with the help of a screw jack. So the entire weight of the car will be acting on this screw spindle. Next, here we can see some of the dimensions. I'll just explain some of them. Like for example, here there is DC and DO. DC indicates the core diameter or the minimum diameter of the screw. DO indicates the outer diameter of the screw. Next, here we have capital D, which we can take it as the diameter of handle. D1, capital D1, it is the diameter of, you can say, outer diameter of nut. Next, D2, it is the diameter of nut collar. D3, it is the outer diameter of head, or you can say the bigger diameter. D4 is the small diameter for the head. Then we have D5, which is the diameter on the outside for the body. D6 is the internal diameter at the base, and D7 is the external diameter at the base. So these are some of the diameters. Then capital H, it indicates the height of head. Small h indicates the height of nut, as it is visible from the diagram. Then we have T1 as the thickness of nut collar, T2 as the thickness of base, or we can say the thickness of the body. Next, if the thickness of base is T2, the thickness of body is taken as T3. Then here we have lifting height. Lifting height indicates the height of the screw in its maximum upward position, that is by how much amount it will lift, and lifting height is equal to the amount by which the load would be lifted to its maximum position. Then we have the entire height of the body of the screw jack, which is called as the body height. Here we have handle length, I can denote it by L. So these are some of the description of the parts of a screw jack. Now let us get started with the design for the screw jack. Here the heading is design procedure of a screw jack. Now, in the design procedure of screw jack, I'll divide it into number of steps. The first step is step number 1. It is called as design of screw spindle. Now, if I look at the diagram of a screw jack, then suppose it is lifted completely and then the load is acting over the screw jack. As we can see, the bottom end of the screw jack is fixed and here the load is applied. So the kind of loading which the screw is subjected to, that would be called as compressive load, because on that screw the load which is kept, it will try to compress this screw spindle. So for the design of screw spindle, I'll say that considering screw spindle under compression. Now when I am considering the screw spindle under compression, first I will draw the failing area where it will fail. Here I am drawing the section. Now this I will term it as the diameter here. I'll denote it as DC, called as the core diameter. Now why we are considering core diameter here? Since we are having a screw spindle, I'll just draw the profile of a screw so that I can explain it in a better way. Here I am drawing the profile of a screw. Now, when we have a screw, as it is clear from this diagram that for screw we don't have the diameter constant. At one end, that is here, we are having a bigger value of diameter. This is called as DO, the outer diameter, and here we have the minimum diameter. This is called as the core diameter DC. So failure will always start at the minimum diameter. Now if I compare out of DO and DC, DC is the minimum diameter, and when the screw is subjected to compression from both the sides, there is compressive load. Because of this compressive load, there are chances of this screw to break along its minimum diameter DC. It will break here. So now, here considering the screw spindle under compression, it will fail along its thread at the minimum diameter, which is DC. So this is the resisting area. So now I'll write it down. Therefore, resisting area capital A, that will be equal to, it is a circular area, pi by 4 into DC square, where DC is the minimum diameter of the screw thread. So I'll write down therefore compressive strength, because I am considering the failure under compression. So compressive strength of screw spindle. Now strength, as we know, it is written in the form of load is equal to stress into area. Here I am getting stress as compressive, so sigma C, area is capital A. So therefore the strength equation W is equal to area pi by 4 DC square multiplied by sigma C. This I'll keep it as equation number 1. This equation gives us the load carrying capacity of a screw jack. That is, if we know how much is the core diameter of a screw spindle, if we know the value of compressive stress, then we can calculate how much is the load carrying capacity for the screw jack. And similarly, if we know the value of load, if we know sigma C, we can calculate the core diameter. So I'll say that therefore from equation number 1, DC can be calculated. So this was considering the spindle or screw spindle under compression. Now after this, once I have considered it in the first step, now as we can see, because of compression this screw spindle can fail along the core diameter, minimum diameter. At the same time, this screw is subjected to a torque because we are holding this handle and then we are rotating it. So when we rotate this handle and at the same time load is kept, so here this screw spindle is subjected to torsional shear stress because of the rotation of handle. So here I'll say that considering torsional shear stress for screw spindle. Now when I am considering the torsional shear stress for screw spindle, I know the formula of torsion. I'll say that therefore T1, I'll write it as T1 is equal to pi by 16 DC cube into tau. Here I am having this equation. This equation I'll call it as the second equation, and this has come from strength criteria. The strength criteria which we are using for the design of shafts, because we can consider the screw spindle as a rotating shaft, and when it rotates there are chances of torsional shearing. So here this equation indicates the torsional shear stress tau. I'll write down therefore tau will be equal to 16 into T1 upon pi into DC cube. Now here from this equation we can get the value of shear stress, but we should also know T1 here. So I'll say that where T1 here, T1 is equal to torque required to rotate the screw, and this torque required to rotate the screw, it can be calculated by using the formula T1 is equal to W into tan alpha plus phi multiplied by D by 2. So from this formula we can get T1. Once we know T1, we can easily calculate the value of shear stress. Now, one more important concept here is that since we can see from the diagram that this screw jack is subjected to compressive load from the top, load is kept and then the screw is rotated with the handle. So there are two stresses which are acting at the same time on this screw, and those stresses are, at first, because of the load there is compressive stress, and because of the rotation of handle there is torsional shear stress. So whenever a particular member or any screw, like in this figure, it is subjected to two stresses at the same time, so we can write it as considering maximum shear stress theory. Now from this theory we can write it as tau max is equal to half of under root sigma c whole square plus 4 into tau square. Because here, as the screw is subjected to two kinds of stresses at the same time, so we can get this maximum shear stress from maximum shear stress theory. And similarly I can write down considering maximum normal stress theory. In this we can write down sigma c max, that is maximum compressive stress, will be equal to half into bracket sigma c plus under root sigma c square plus 4 into tau square. So now here in step number 1 we have reached at this stage where we are getting the maximum shear stress tau max, and we are getting the maximum normal stress, that is sigma c max, which is called as maximum compressive stress. So we can check these values from this formulae for the screw spindle, and here with this we have completed the step number 1, that is the design of screw spindle. Next, as we see into this screw jack, after screw spindle, the next part which we have to design is the nut. Now here we are having this nut, we need to design it. So I'll write down here, that is step number second, it is design of nut. Now in the design of nut, the first consideration is considering bearing failure of nut. When we are considering the bearing failure, here I'll draw the diagram. Of the resisting area. This is the area which is subjected to bearing. Outer diameter is DO, inner diameter is DC. Now, how this bearing failure takes place? Since screw and nut, they are in contact, so there are chances when we see screw and nut, they are in mesh, they are in contact. So there are chances of rubbing between the screw and nut because of the compressive load and because of rotation. There is continuous rubbing of screw and nut, and because of that rubbing, what happens is that the portion of the nut, it can crush like this. So here, if I can explain it in a more simplified manner, here I'll draw the profile and explain. This is the screw profile which I am drawing. Screw and nut. Now, this portion is the nut, and here we have a screw. So when both are in contact, there are chances of rubbing of the portion here. That is, metal powders would be formed because of this bearing action. So the area which is resisting bearing, that I have drawn here, this is the resisting area. So therefore, resisting area, capital A, it is equal to area of a hollow circle, pi by 4 dO square minus dC square. And now I can say that therefore bearing strength of nut, it is W is equal to area multiplied by bearing pressure so therefore W is equal to, here the area is, I'll write it down, pi by 4 into dO square minus dC square. Now this is the area of contact between one pair of screw and nut. Like this we have n number of pairs, so I'll write down it is into small n multiplied by bearing pressure. Now after this I can say that therefore from above equation small n, and what is small n? It is number of threads in contact. So from the equation here I can get the number of threads in contact. It can be calculated, and once I know the number of threads in contact, here I can even calculate the height of nut here, which is small h. So I can say that therefore height of nut small h is equal to n multiplied by p, where this p indicates pitch of screw thread, and this pitch will be in terms of mm. So now once we have designed the core diameter of the nut, we have designed the outer diameter for the nut, and we have designed the height of the nut. So this was considering bearing. Now the second consideration is considering tensile failure of nut. This design procedure is quite lengthy. Considering tensile failure of nut. Now when we are considering tensile failure, as we can see from the diagram of the nut which I have drawn here, this is the maximum diameter called as DO, and nut will fail along this maximum diameter, that is along DO. So what happens is that when the compressive load is acting, this screw spindle is in contact with the nut. So there are chances of this screw spindle to stretch the nut, and then the nut will be failing because of tension. So here I'll say that considering tensile failure of nut, the area which is resisting tension that area I am drawing here. Next, considering tensile failure of nut, here I will write the outer diameter as this is D1, and here the failing area is this section. Here I am marking this diameter. It is DO, which is the outer diameter, or we can say major diameter, and nut will fail along this diameter. So here is the resisting area. So considering tensile failure of nut, resisting area capital A, that is equal to pi by 4 D1 square minus DO square, that is area of this hollow circle. Therefore tensile strength of nut, it is W is equal to area multiplied by tensile stress Therefore W is equal to, area is pi by 4 into d1 square minus do square into sigma t. Therefore we can say that from this equation, d1, that is the outer diameter for nut, here as we can see in the diagram, this d1 can be calculated. So here we complete the second point in step number 2, that is the design of nut. Here what are the things we have designed, I'll just give an overview. In step number 2 we have designed the height of nut and we have designed this outer diameter of nut d1. Now next, here I will be designing the thickness of this nut collar, and for that I will consider the shearing of nut collar. The next consideration is considering shearing failure of nut collar. Now there are chances that this nut which is having outer diameter d1, when the load is applied, screw will pull this end, and what can happen is the nut can shear at this junction. So here I'll write the shearing area, that will be pi into d1, which is the circumference at this location, multiplied by thickness t1, that gives us the shearing area. So therefore shearing area, capital A, it is equal to pi into d1 multiplied by t1, and therefore shearing strength of nut, that is W, is equal to area multiplied by shear stress tau. Therefore W is equal to, area is pi into d1 multiplied by t1 into tau So now I can say that from this equation, T1, that is the thickness of nut collar, it can be calculated. Next, after considering the shear failure of the nut collar, there are chances that even the thread between the screw and nut, as they are in contact, so this thread they can shear off for the nuts. So I'll say that first I had considered shearing failure of nut collar. Now I'll write down considering shearing failure for threads in nut. Now when I am considering the shearing failure, I'll draw the diagram here and explain. I am drawing the profile of the nut. It is in contact with the screw. Here I am drawing the profile of screw and thread. The nuts which are in contact. Now, as we can see in this diagram, here this is the nut and here we have screw. So there are chances that when the load is applied, there can be shearing of this nut along its major diameter. It can fail here, which is called as DO. So the failing area is, I'll write down, since resisting area, it is also called as the failing area, that will be equal to pi DO, which is the circumference, multiplied by T, which is the thickness of threads. And therefore I can say that from this, shearing strength of nut, now that strength is equal to area multiplied by shear stress, because we want shearing strength, so therefore W is equal to, area is pi DO into T multiplied by tau, where T is equal to thickness of each thread, and it is taken as pitch by 2 distance in terms of mm. So here I'll say that from this equation, T, which is the thickness of thread, can be calculated, or if we know the thickness of thread, then we can check the value of shear stress from this equation. After designing the nut, the third component that we will design in step number 3, that is the handle. So here, step number 3, in which we have design of handle. Now when we are designing the handle, at that time we should know how much is the torque. Torque means torsion, or we can say the quantity which causes the rotation. So how much is the rotation effect produced? So I'll say that in the design of handle, the first step is total torque applied at the handle. So that total torque applied at the handle, it will be capital T is equal to T1 plus T2. I'll give this as equation capital A. So here I'll mention what are these terms, where T1 is the torque required to rotate the screw, and T2, it is the torque required to overcome friction between nut collar or here I can say that we are overcoming the friction since we are placing this cup. Because of this cup, here as we can see there is some bearing area, so we need to overcome the friction here, because cup is placed on top of the head to prevent the rotation of the load. And when we are applying the torque here, some value goes into the rotation of the screw and some amount of torque is required to avoid the rotation of load here. So we are overcoming the torque here, which is T2. So it is to overcome friction between cup and head. So here I'll mention the values that therefore T1 torque required to rotate the screw, the formula is W into tan alpha plus phi multiplied by D by 2, where D is the mean diameter. Next, T2, it is equal to mu W Rm, which is the torque required to overcome friction between cup and head. So Rm, I'll write it down here, where all the values I'll denote it, where mu, here I have written it is mu W Rm, I'll denote it by mu1 to differentiate between the coefficient of friction, because mu will be the coefficient of friction between screw and nut, mu1 will be the coefficient of friction between cup and head at this surface. So coefficient of friction have two different values. So here mu1 is equal to coefficient of friction between cup and head. Next, W, as we know, it is the load which is kept on screw jack. Now the term R suffix M, it is called as mean radius, and for Rm we have two different values. So I'll write down the first value. Rm is equal to, here D4 is the minimum diameter and D3 is the maximum diameter. So from the center, if I take the distance, R3 becomes, from here till here, R3 is the major diameter and R4 will be the smaller diameter. So this section is hollow. So for that I'll explain it here. This is the bearing area. Here outer radius, that is R3, inner radius is R4. So Rm is equal to, it is R3 cube minus R4 cube upon R3 square minus R4 square. So this formula which I have written, it is by uniform pressure theory. And in this same formula, after writing this, I'll have to write it as Rm, multiplying it by 2 by 3, and this is the complete formula. So now, after I have written the formula by uniform pressure theory. Next I'll write the formula by uniform wear theory, and that will be R1 plus R2 by 2, or here R1 is nothing but R3 and R2 is nothing but R4, so it is R3 plus R4 by 2, and that is by uniform wear theory. So once I have written both these formulae, I can easily calculate the value of torque T2, and once T1 T2 are known, we can put them in equation number 1 and get the value of T. So now after this, since we are designing the handle, I can say that therefore total torque, after getting the value of total torque, it can be written as P multiplied by L, where P indicates the effort, capital P, it is the effort applied at the handle, and a normal person can apply a load of around 300 to 400 Newton by his hand. So here I'll take this value of P, it can be from 300 Newton to 400 Newton. Next, once I know the value of P and total torque, I can say that therefore capital L, which is the length of handle, it will be T upon P. So in this equation, I'll say that from this equation L can be calculated, that is here we can get the length of handle. Next, after getting the length of handle, I can say that therefore bending moment is given by, the formula of bending moment is M is equal to pi by 32 d cube into sigma b. And from this bending moment equation, here we can get from this equation diameter of handle, which is D, it can be calculated. So here in this step number 3, we have designed the length of handle and the diameter of handle. This diameter we have designed, denoted by small d. So here we complete the step number 3, design of handle. Now the last step, which is there in case of the design of screw jack, now we will write the value of load at which this screw will try to buckle, which is called as the critical load. See, what is the meaning of buckle is that when the screw is lifted to its topmost position, that is about this entire lifting height. Here in the diagram we can see the screw jack in the bottommost position. Now when it is in the topmost position, this end of the nut here will be attached here, and this screw would be entirely lifted. So when it is completely lifted and when the load is applied over the screw, then it is a case of buckling. The screw will buckle in the lateral direction. So for that I'll write down, in step number 4, checking buckling of screw, spindle. Now in this case I'll write down, therefore buckling load or crippling load is given by, here I have the formula, that buckling load, or I can say it is crippling load, it is W suffix CR, and that is AC into sigma Y 1 minus sigma Y upon 4C pi square into capital E multiplied by effective length upon K square. This is the formula of buckling load. Here I'll say that I'll define the terms where A suffix C, AC, is the cross sectional area of screw at core diameter. Unit will be in terms of mm square. Sigma Y, it is called as yield stress. Next, LE, it is called as effective length of screw spindle. C, it is called as end fixity coefficient. And its value is 0.25. Then K, it is called as radius of gyration. And radius of gyration, it can be written as root of moment of inertia upon area. So from this value, here we can get from this formula the value of critical load, and that critical load is the load when which is applied to the screw jack. This screw spindle will buckle, and the meaning of buckle is that this screw spindle will bend in the lateral direction, forming a curve. So that condition needs to be avoided. So here, once we know this critical load, we will divide it by factor of safety and get a safe load, which would be the design load for the screw jack. So here in this video, in 4 simple steps, we have seen how to design a screw jack, starting with the screw spindle. Then we had gone onto the nut. After that, we had designed the handle, and at last we had designed the critical load which the screw jack can carry. I hope everything is understood in this video.